Average acceleration. It is defined as the change in velocity divided by the time interval during which the change occurs. It is given as A average or A bar. It is written as A bar, but you should read it as A average equals to V2 minus V1 divided by T2 minus T1 equals to delta V by delta T, where V2 and V1 are the velocity of particle at time T2 and time T1 respectively. Similarly, we can define instantaneous acceleration. Instantaneous acceleration, it is defined as the limit of the average acceleration as the time interval delta t goes to 0. That is, instantaneous acceleration is simply written as A equals to limit delta v by delta t and delta t tends to 0 and equals to dv by dt. So it is clear that when we take the limit on the average acceleration and makes time interval tends to 0, that will becomes instantaneous acceleration. Now both acceleration is a vector quantity. It may be positive, negative or 0. Here positive, negative, it shows the direction of acceleration, but when we take the magnitude of acceleration, then it will be only positive. Now unit for acceleration is meter per second square, SI unit, and dimension is written as a dimensional formula L T minus 2. And the next term is, if the body moves with constant acceleration, then average acceleration is equal to instantaneous acceleration. Also in velocity time graph, the slope of the line passing through 2 points give the average acceleration during this time interval. Here a graph is shown between velocity and time, and we take origin at a reference point, and we have to take the average acceleration between point A and point B. Then we draw a perpendicular here, and it cross the time axis as 10. And when we and then simply we draw a straight line from O to B, so that we can find the tan theta, which will give the average acceleration, because we know that the slope of line in a graph, velocity time graph, gives the average acceleration. So where here average acceleration, slope of line OD, this average acceleration is between time interval 0 to 10 seconds. So slope of line OB equals to tan theta, which equals to BA divided by OA, AO, and that will be BA is equal to 24 and OA is equal to 10, so it becomes 2.4 meter per second. Or for example, in the above graph, the average acceleration between the time interval 0 to 10 seconds, A average will be 24 minus 0 divided by 10 minus 0. Same answer will come 2.4 meter per second square. Now, acceleration occurs due to change in the magnitude of velocity, direction of velocity, or due to change in both magnitude and direction. Next point is sign of acceleration in the position time graph will be as like, if the graph is like this, this is the position and this is the time axis and this is the position axis, then if the graph is like this, then the acceleration will be positive. This represents the positive acceleration. If the graph is like this represent position axis and this represent time axis, then this graph here represent that acceleration is negative. And if the graph is like a straight line in position time graph, then it will represent zero acceleration. That is, there is no zero, there is no acceleration, body is moving with constant velocity. Next, in velocity time graph, area under the curve represents the displacement over a given time interval. For example, here a graph between velocity and time is drawn, and body start with velocity v naught, initial velocity at time t equals to 0, and in time interval t it reaches at point A. Here point A, here is C, v naught, this represents a graph, and t is equal to 0, the graph represents the velocity v naught, and t equals to t represents the velocity at v. The area of the rhombus OV naught AB represents the displacement of the particle in interval time interval 0 to t. To prove it, let's consider For proof it, let us consider a body is moving with constant velocity u. The velocity time graph for this motion is shown in the figure here. Velocity time graph. It starts with initial u velocity, so graph is like this. And this is the time axis. The area of the velocity time graph for this motion is shown below. The area of rectangle OABC equals to OA into OC, where OA represent U and OC represent time interval t. So U into t, ut, and this is that is velocity into time represent displacement. So it is equal to displacement of the particle in time interval t. So in velocity time graph, the area under the curve represent displacement in a given time interval. Now kinematic equation for internally accelerated motion. These are the equation: v equals to v naught plus at for accelerated motion. Consider a body moves with constant initial velocity v naught, and after time t second its velocity becomes v. Then by the definition of average acceleration, we have average acceleration a equals to change in velocity divided by time interval, or a bar equals to v minus v naught by t, or a equals to v minus v naught by t, or we multiply cross multiplication, the v equals to v naught plus at. This is proved. Now the next kinematical equation is x equals to v naught t plus half at square. Let us draw the velocity time graph of the above motion. Here it is shown the velocity time graph. At t is equal to 0, the particle has velocity v naught, and at t equals to t, the particle has velocity v represented by point V, and initial velocity represented by point A, and this is the time interval. and this is time axis and this is the velocity axis. We know that in the velocity time graph, the area under the graph gives the displacement of particular object. Hence, displacement of object in time interval t equals to area of O A B C D O. O A B C D O. This area will give the displacement of the particle, or x, because displacement is represented by x. So x equals to area of OABCD. Now this area can be divided into two parts: area of OACD plus area of ABC, area of OACD, and this is rectangle, and plus area of ABC, this is triangle. Now both area can be calculated. So area of OACD is V naught into T, and plus area of ABC 1 by 2 into T into V minus V naught. But we have A equals to V minus V naught by T. This implies V minus V naught equals to AT, equation 1. Using 2 in 1, we get x equals to V naught T plus half T into AT. Using 2 in 1, we get x equals to V naught T plus half T into AT, or V naught T plus half AT square. So x equals to V naught T plus half AT square. Again, from equation 1, x equals to V naught T plus half T into V minus V naught, V naught T plus half Vt minus half V naught T equals to half V naught into T plus half Vt equals to V naught plus V by 2 into T, or equals to V average into T, equation 3, where V average equals to V naught plus V by 2 equals to average velocity, equation 4. So this is the uh, so we have calculated uh, two formula uh, for displacement. The first one is x equals to V naught T plus half AT square, and the second one is x equal to V average into T, where V average is V naught plus V naught plus V by 2. That is average velocity. Now the next equation is next is V square equals to V naught square plus 2x. Next kinematic equation. So we have from equation 3, x is equal to V average into T equals to V0 plus V, or V naught plus V by 2 into T. Putting value of T from 2 in above equation, we get x equals to V naught plus V by 2 into V minus V naught by A equals to V square minus V naught square by 2A, or this simply equals to 2ax equals to V square minus V naught square. Hence V square equals to V naught square plus 2ax. So we also proved this equation, that is the kinematic equation come out to be V square equals to V naught square plus 2x, where V is the final velocity, V naught is the initial velocity, A is the acceleration, and x is the displacement for one dimension motion.